Hey guys, so this is a recorded lecture on schematics. You won't find a lot of source material for this in the Bouchon book. They have stepped away from actually explaining the circuit elements. You might see some explanation of the circuit elements piecemeal, but just as I was building this and revising it for recording, I noticed as I skimmed through the chapter for the X-ray circuit that it's really sad. They kind of stopped explaining individual piece components and demonstrating the symbols, and really give you a good base background in electrical engineering, which is an added practical benefit to this program that other programs don't feature. And so, for example, after I became the instructor to this physics course and insisted that we actually tear apart the schematic into its components and we learn the components and their functions and their symbols, I learned enough about electricity that I was actually able to wire a 220 volt high voltage line in without burning my house down by myself under my crawl space to install a hot water heater in my son's bathroom. And I didn't have to call a plumber, and I didn't have to call an electrician because I was able to do that by myself and with my father-in-law. So that's the power that I'm about to unleash on you, the understanding that you're going to have of this X-ray schematic would be an equivalent understanding that an electrician would have of the same drawing. Okay, but it starts with you understanding what the symbols mean. And there is another electrical device, battery-powered electrical device, that we use to survey for radioisotopes and contaminated areas where radioactive material may be in the environment, specifically nuclear medicine. That's called a Geiger counter. A Geiger counter actually utilizes a lot of these simple schematic symbols and these basic circuit elements. There's a lot of the elements that I'm going to tell you about in this lecture are fairly universal. Almost everything has these devices in it in some form or fashion. All right, so what are my objectives for this slideshow? Oh, and instead of us hosting class on April the 8th, I will be in upstate New York with my family watching a total solar eclipse. Just fun fact there. Provide representative examples of various schematic symbols. Name and give a brief description of the function of each circuit element. Demonstrate the function of a simple circuit relevant to X-ray science, the Geiger counter. So let's get into it. Our first schematic symbol is a battery. Now, batteries are stacked in cells, so each individual unit, you see how I've got 2 units on the left side and then 1, 2, 3, 4, 5, 6 units on the right side. Okay, those are cells. Batteries are composed of cells. The more cells you stack in series, the higher the voltage the battery can generate. So if the cell on the left was, let's say that was a 6-volt battery, that would mean each cell, the long bar coupled with the short bar, is providing 3 volts. And if the battery on the right was of the same fashion, then I would have 3, 6, 9, 12, 15, plus 3, 18 volts on the battery on the right if they were of the same component strength. Okay? And so each cell provides an additional fixed amount of voltage. Batteries are the source of what we call direct current, and we're going to watch a movie, War of the Currents, where you're going to figure out that Edison was backing a direct current electrical grid that was kind of non-practical. The current only flows in one direction. The trouble with direct currents are that as the wire gets longer and longer, the resistance builds, and so the current wanes for long distances. But for portable electric circuits like cell phones and X-ray portable machines and things of that nature, a battery is a perfect power source because it is portable and convenient. So in a direct current, current only flows from one direction. The battery has a cathode and an anode side. The anode side is the positively charged side, and the cathode side is the negatively charged side. And the current is said to flow from positive to negative. Okay, and hopefully you've had the electrodynamics lecture where I teach you about the direction of Franklin current. Franklin current will also come up again in this lecture. So a battery usually relies on a chemical reaction and two different metal plates. That's what the short and the long lines are for, are the anode and cathode metal plates. And you soak those typically in an acid solution with a sodium salt of the acid. So like your car battery, or not the sodium salt, so it's either the sodium salt or another metal salt, and typically it's one of the electrodes. So the car battery is a lead acid battery. One of the electrodes is lead. I think the other one is either copper or aluminum, maybe nickel, I'm not sure. And then the acid bath that the cathode and anode are swimming in, that acid bath is hydrosulfuric acid. Okay, so it's lead is one of the diodes, and then another alternate metal, maybe even zinc. Zinc is a common alternate metal in batteries, and so the lead and the zinc metal are submerged in a bucket of acid. That's why batteries are so heavy, is because they're mostly aqueous media, acidic aqueous media, and so you get lead sulfur salt dissolved into the hydrosulfuric acid, and then the reaction between the lead and the zinc and the acid in between them creates a movement of positive charges through the acid, depositing on one of those two metals, and in effect stealing electrons from that metal. And then the opposite type of reaction happens on the other side, and what happens is if you connect a conductive wire from the cathode end to the anode end, it drives the chemical reaction, and you get to push electrons down the wire in one direction. Now, a battery is made up of multiple cells. Typically, every cell that you stack in series adds to the overall voltage or the pushing power of the battery. Now, the chemical reaction can only be accelerated so much before it comes to an upper limit, and so there's an upper limit for a battery, an individual battery that you buy. It's always got a voltage rating, and so it's called nominal voltage. And so when the battery is fresh and the chemistry is robust, and the reaction can readily occur, you're going to get like 1.5 volts or 3 volts or something like that. If you stack more cells, you'll get more volts, all the way up to I think 50 or 100 volts is reasonable. But there is an upper limit to how potent you can make the battery as far as the voltage supplied, because it is based on creating and then neutralizing ions in the battery acid. Okay. Capacitors, notice that there's not an alternating long and short metal plate. There's just two parallel metal plates with a little gap in between. Capacitors act as temporary batteries in that if you push voltage to a capacitor, you'll actually start stacking charges, opposite charges, on either side, either one of those big metal plates. So you'll have positive charges on the one side, and that becomes the anode, and excess electrons on the other side, and that becomes the cathode. As long as the gap is sufficient, the charges will hold themselves on the metal plates, but they won't discharge across the gap because the gap is sufficiently wide enough. As the circuit loses power, that is, it's disconnected from other power supplies, the capacitors drain charge to create new voltage, to ballast the voltage from dropping off when other devices like batteries or AC generators are shut off and are no longer providing electricity to the circuit. Some portable machines store charges in several capacitors and discharge them during exposure. So if you work with a portable machine, you might notice some funny sounds coming out of it during the exposure. That the exposure alarm whistle is probably not going to stay in one tone. That's because a lot of portable machines are capacitor array discharge portable machine. There we go. Diodes. This is a diode. Diodes are devices that only allow current to flow in one direction. So intuitively, if you look at this, right, there's an arrowhead and an arrow coming from the anode and going to the cathode. Okay? Now, which way does current flow through this thing? From positive to negative. What? Well, the convention that we've learned, electrons flow opposite the divine direction of current in metals, is because Ben Franklin screwed it up. He made the rules such that any electricity flowing out of the wire was positive, and it's giving that back to the ground. Okay, and I got a link there explaining how Ben Franklin screwed it up. But I also have this little cartoon. We were going to use the time machine for preventing the robot apocalypse, but the guy who built it was an electrical engineer. And so this is an electrical engineer going back in time to meet Ben Franklin. Yes, I bring a message from the future. I don't have much time. Well, what is it? The convention you're setting for electric charge is backward. The one left on glass by silk should be the negative charge. That would fix everything. And so Ben Franklin was an early experimenter, along with Auguste de Coulomb and I think Gauss and Oersted and Faraday. All these guys were experimenting with electric charges and electricity. Ben Franklin was the one that first theorized that there were charges present on charged objects, and you could charge objects by friction sometimes, and then you would see a discharge once the friction device was removed. And so Ben Franklin said, well, electricity must be flowing from abundance to deficit. And that was his convention. And so abundance of electrical fluid, if you will, as Ben Franklin said, is that's a positive. That's overall, that's a good thing. But a deficit of, quote, electrical fluid is a negative. Well, he got it exactly wrong. And so the definition of Franklin current is not from the electrons to the X-ray text. The definition of Franklin current is just, you are a grown adult. You went over and set the control panel for the machine. You hit the exposure button. I don't want to hear anything about it accidentally. Okay? There is no accidentally. You know exactly what you're doing. You just choose to do it on autopilot, and then you made a mistake. How about next time, don't choose to do it on autopilot. All right, our next symbol is the ground or ground wire. A grounding wire is a connection to a source of infinite charge. Usually that's just a large object with lots of available donor electrons in their atoms. The best ground is the Earth. That really is a reservoir of infinite charge. In the scale of the charges that are moving around a simple electric circuit, the Earth does have an infinite reservoir of charge in that specific context. All right, so grounding wires typically can be the metal chassis or housing to the machine, or a connection back to the building's foundation, which is the third prong on the plug typically. Grounds will allow for the circuit to borrow or dump electrons as needed, and what that does is it ballasts the current and keeps the current from skyrocketing, and it avoids overloading key elements of the circuit when you ground out the circuit, and overloading of those elements would cause those components to be damaged from too much current. A circuit breaker, it does exactly what you think it does. It breaks the circuit. Okay. Circuit breaker is a double switch. It breaks the circuit if the amperage exceeds the safe threshold. If the current flow rises excessively, the circuit breaker's internal switch is tripped, stopping the flow of electricity. Circuit breakers prevent electrical fires. If you don't have a circuit breaker that automatically kills the circuit when there's too much amperage on the line, well, amperage leads to heat, and heat leads to components cooking inside of walls, catching fire. So be mindful of that. A resistor is a device designed to inhibit the flow of electrons. Therefore, it regulates the flow of electricity through the part of the circuit where it is placed. Resistors offer resistance to the flow. Okay, they do this as a safety measure because, just like the circuit breaker, the resistor is trying to keep the amperage under control. Amperage is the source of heat in the electric circuit, and so if the amperage is way too high, then the circuit will overheat and potentially cause a fire or damage components with too much amperage. It really is. It's dependent upon what machine you're running and what current it likes to take versus what current are you offering it. Okay. Meters. Amperage, we overlapped a little bit. Amperage is what's in parentheses there. Ammeters will measure current or amperage, but they must be wired in series in order to represent the magnitude of current elsewhere in the circuit. The reason for that is amperage is constant in series. And so if you want to measure the current across the X-ray tube, you can't do that inside the X-ray tube, but you can do it right next to, either right just before the X-ray tube or just after the X-ray tube. And what you do is you just wire in an ammeter, and so that the current before it reaches the X-ray tube or before it exits the X-ray tube, well, actually just after it exits the X-ray tube. God, that's a tongue twister. The ammeter wired in series back to the power supply will report a current flowing through it. The current that's wired in series predicts the current of all other circuit elements that are wired in the series arrangement with that ammeter. In similar fashion, the voltmeter must be wired in parallel because voltage is constant in parallel. In order to make a prediction about voltage elsewhere in the circuit, the voltmeter needs to be wired in parallel to any circuit element you want to know about. Okay? And so, yeah, those are the two big ideas and the definitions there about how current is constant in series, but voltage is constant in parallel. That'll help you remember where to place the ammeter and the voltmeter in the X-ray schematic, which is coming up. Okay. Our AC power supply, we covered the battery as one of the first symbols we did in this lecture. That was for direct current. If you're plugging a device into a wall, like a vacuum cleaner or a table fan or a blender or a coffee maker, it's wired to the electric grid. It's not just magic that you plug it in and it works. No, the electricity has to be supplied at the junctions, okay, or the plugs, if you will. Okay. The United States electrical grid, when it shares electricity via transformers and then back into buildings, and buildings have electrical power, the default mode of alternating current is, the default mode of electricity transition is alternating current. Okay, so if you're plugging something in, that means you don't need for it to be mobile. That means you can use long wires if you needed to, and that way you can use long wires if you wanted to. And with alternating current, you don't get a depreciation of voltage or current with distance. The reason you don't is because you're making the electrons kind of oscillate or cycle or drift back and forth in both directions along the conductor wire. So the electrons free on the outer surface of the conductor will drift to the right, and then they'll slow down, and then they'll drift back to the left, and then they'll slow down. And every time they move, they're technically accelerating, and then you can capture the kinetic energy of accelerating electrons. All right, rectifiers. Now, I covered diodes, or maybe I didn't. Maybe it's coming up. Yeah, it might be coming up. Probably should have changed that order. Well, too late now. Rectifiers are geometric arrangements of diodes. Now, so we see what I would call a 4-diode diamond rectifier here. That's the one you're going to need to memorize for the schematic. Rectifiers are also called diode bridges by some authors. It's the same thing. Okay. What a diode bridge or a rectifier does is it takes in alternating current, but then it broadcasts or pushes out direct current. And the way that it does that is it redirects electrons down one-way streets. That's what diodes are. And so diodes can only conduct electricity in one direction, and they force the alternating current to move like direct current by changing the way that it flows. So a rectifier, we'll cover this later in the X-ray schematic, but the inputs are in the top of the diamond and the bottom of the diamond, and then the outputs are at the left and right sides of the diamond. So let's say electrons are coming in through the green at the top. Well, a diode is only going to allow the electrons from green to flow to the left and exit red. Okay? And same thing for orange. If electrons come in at orange, again, they're only going to be allowed to flow to the left and exit at red. Okay? And so no matter which way electrons come into the ring, they can only exit red. So negative charges can only exit red. Now, let's do the same thing with positive charges. Okay? Positive charges coming in from green can only go to the right because of the diodes. Those are one-way streets. So a positive charge heading to the right will exit blue. Okay? And let's do orange. Positive charges coming in from orange. Again, they can only go to the right because of the one-way streets, and has to exit blue again. So for all scenarios, either negative charges coming in from above, green, or positive charges coming in from above, and then negative charges coming in from orange or positive charges coming in from orange. The way this bridge works is negative charges can only exit the diamond via the red color, and positive charges can only exit the diamond via the blue color. In other words, direct current. So the input is alternating current, the output is direct current. And we will bring that back when we discuss the X-ray schematic. Now this isn't really a circuit element as much as it is how do you arrange your circuit elements. And so the first orientation, or first simple orientation, because these two orientations can and will be combined later on to form a more complex circuit, is a series geometry. In a series geometry, all the circuit elements are lined up one after the other on one pathway, and the pathway does not split. So in order to get back to the battery, it's got to go through all the circuit elements one at a time. Okay, so that's the electrons. Okay, this kind of functions like a one-lane road, and just like a one-lane road, the electrons can only travel as fast as the slowest electron on the circuit. Now, parallel geometry, you might say, why did I turn that picture on its side? And that's so you can see that it's shaped like a ladder, and the branches are the rungs of the ladder. Okay, and so parallel arrangements stack circuit elements on independent branches. And so we have resistor 1, resistor 2, and resistor 3 here, and a battery at the bottom between 1 and 8, pushing electrons in the direction of the arrows. Okay? And so the electrons flow up from 8, and when they get to 7, they have a choice. They can cross resistor 1, or they can continue on to resistor 2 and 3. And then the same thing happens at 6. Again, they have a choice. They can cross at 6, or they can continue on to 5 and resistor 3. And so what you get is the electrons choose the path of least resistance. The resistor has got the least resistance, has the most current, and then the resistor that has the most resistance has the least amount of current, because the electrons are not going to wait around. It's not a one-lane road, and if there's an electron going slow in front of it, it's just going to take an alternate route. That's what the branches are for. Now, a nice thing about parallel geometry as far as the usefulness goes, parallel geometry is the expensive Christmas tree lights, because if you get the cheap ones, how are they wired? That's right, in series. So if you blow one bulb on a cheap set, do any of the other bulbs light up? No, because you've broken a circuit element and there's only one pathway, and if you've broken that light bulb, then you don't get to conduct electricity through the rest of the pathway. Okay, but on independent branches like R1, R2, R3, we can set fire to R1 and totally disable it. Electricity will still flow through R2 and R3. In fact, more electricity will flow through R2 and R3 if R1's pathway is not available anymore because of damage or whatever. Or you can just pull it. Okay? And so what happens with the expensive Christmas light bulbs, if you're paying attention, if you blow a bulb, what actually happens is the rest of the bulbs get just a little bit brighter. And so that's the advantage. Parallel geometry is the preferred geometry for strings of Christmas lights. Resistors that are arranged into an array of increasing strength. Remember, resistors impede the current. And if it's selective resistance, like because you have several resistors stacked and you can choose which one you want to go to, that's called a rheostat. And so a rheostat is also called a variable resistor. You see that if you look on the internet for some of these diagrams, you'll see that. Now, an electrician is going to use the top symbol here, but Mr. Bouchon uses the bottom symbol. They mean the same thing. The arrow means choose the magnitude, and then the symbol resistor is behind it. So the top symbol literally means choose the magnitude of your resistance. And so everyone knows that device is called a rheostat. Now, Bouchon's symbol diagram actually shows a multi-point switch and the array of resistors that I mentioned. And so Bouchon's diagram of a rheostat is closer to what it actually looks like if you were to view a rheostat. A switch, everyone is familiar with a switch, yeah, like a light switch, yeah. So when you turn the switch off for the lights stop glowing, but did you ever stop to ask why? Why did lights stop glowing? Well, that's because electricity, what we learned in electrodynamics, needs three components. It needs a source of electrons, it needs a way to push or pull on those electrons, and then the last component of electricity is a closed conductive loop so that the electrons can spin back around to where they came from. Okay? Which doesn't seem to make sense, but yeah, that's the way it works. So a switch is a device that opens the circuit, breaks the pathway. Now, this is not the same as a circuit breaker. This is more end user function. If you want the circuit to be on and you want your light bulb to light up, then you got to close the switch. If you want the circuit to be off and the light bulb to be off, then you have to open the switch. Okay? And so that's a symbol for the switch up top, and then a transformer. Transformer is actually two independent circuits brought in close proximity to each other. And so what we figured out with transformers is they can transform voltage by making coils of wire around a iron magnet and passing current through the first coil. You'll actually induce a current in the second coil because of the moving magnetic field of the first coil. Now, why does the first coil have a constant moving magnetic field? Well, that's explained by Faraday's law. And I can give you a crash course in Faraday's law. It basically says changing magnetic fields. If conductors are exposed to changing magnetic fields, then those conductors will start pushing electrons through them, and so therefore you will get current from changing magnetic fields. Okay? So transformer capitalizes on this. It has a primary coil, and it runs electricity through that, and that allows for the production of a magnetic field when you run electricity through a coil of wire. And that electricity is what spawns a new current, or not electricity, the magnetism, the changing magnetic field, is what spawns a new current on the secondary coil of the transformer. Now, the next lecture that I do, we are doing double lecture today, or for the vacation. The next lecture I do will go into more depth about the transformer and explain the transformer law to you. All right. Now finally, this one won't become useful until the fall, so you can put this one in your back pocket. But an ionization chamber is a cathode and anode like a capacitor, except for, unlike a capacitor, you actually seal that off into a glass envelope and you fill the glass with like argon or nitrogen, because that'll ruin it. But that's an ion chamber. If we have positive charges at one end and negative charges at the other, that indicates that the one plate is cathode and the other is the anode. Okay. Now, we have nitrogen atoms in the middle there. If they get struck by radiation, the photoelectric effect and the Compton effect will both do what to those atoms? That's right, ionize them. And so when air becomes ionized, in this scenario, the positive ions will move inferiorly to the negative electrode, the anode, and then the negative ions will move superiorly to ungum the top electrode, which is the permanent electrode. All right, are you ready? So this is a schematic for a Geiger counter, or this is actually just a drawing of the Geiger counter. The schematic comes next. And so I want you to see key components here. First of all, we got an electromagnetic wave at B coming through the window. I hope you guys can see that photon. Now A is considered the outer layer and the inner layer of this ion chamber. Okay. A is connected to a wire and is connected to the cathode side of the battery. Wire, well, we don't really have wire B. Maybe it's wire C. Wire C is the anode side, while the outer layer is the cathode side. And so with an ionization event like Fe, right there, the photon come in and ionized the my badge and the molecule, which is ridiculous. And so F and E create an ion pair when there's a photoelectric event. If the center rod is positively charged, that is, it's an anode, then you'll see current counts start to increase, even with existing radiation dose. Okay. Now, just go through the rest of the piece parts. C is probably that metal wire in the middle. D is the big blue ball, that's a nitrogen atom. And then F is an electron, and E is a positive ion. And that completes the picture. All right, so here's the full schematic for the Geiger counter. We have the ion chamber that it just went over. And there's, at letter H, there's a rheostat wired in parallel to the counter device. And then letter G is a ground just below the battery. The battery is 500 volts, and so you push electrons up to A, and those charges stack on the inside cylinder. When a photon arrives at B, it ionizes one of the nitrogen atoms, D, and it turns into an electron, F, which deposits on the center metal rod, and then a positive ion, E, that neutralizes itself on the extra electrons that are bleeding in from A. Okay. Now the selective resistance in parallel is going to, if the resistance is high at H, Most of the electrons are going to choose to go through the Geiger counter. Could also damage components if we do that. Excuse me. So H, if we select higher resistance, less electrons will choose to go through the higher resistance and more electrons will choose to go through the counter. And so the counter becomes more sensitive, not by playing with the voltage, but by adjusting the rheostat. Okay. All right, I think that's all I have for you guys. I'm going to close this up. There is a summary slide at the next slide, but I'm just going to pass on through that and call it quits. You guys can read the summary of outcomes and the objectives and understand that I covered all of that. So will you see the Geiger counter schematic on an upcoming quiz? Yeah, you might. I just labeled the whole thing, so hopefully you were taking notes. Y'all have a good weekend. I'll see you later.